Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video examines properties of different sampling distributions. Let's get started. So in the previous mini lecture, I'm assuming you watched that before you watch this one, you should remember these results that we got from performing our dice roll simulation. So for 100 rolls of the dice, here's our sample mean, variance, and standard deviation. You can see how those numbers change as we increase our sample size to 1,000 and then again up to 10,000. We notice that about half of the outcomes are above the mean, half are below the mean. That's what we would expect to see. We would also expect to see that as we start taking samples and getting more and more outcomes in our sample, that the value for our sample statistic will jump up to be about where half are above the mean, half are below the mean. And then as you go on and continue to have more and more outcomes, it'll oscillate, but eventually it'll settle upon some value that represents the value of the population, which we got by calculating the expected value. So we also saw that around 1,000 is where these numbers start settling in to the expected value that we saw before. So after about 1,000 rolls of the dice, we get a sample that's large enough to be very representative of our population. Let's take a closer look at the sample mean. So if we make a histogram of the individual outcomes in our sample space, we get a uniform distribution. And this is what we would expect to see. We would expect to get as many 1s, as 2s, as 3s, as 4s, as 5s, as 6 when we roll the dice because we're using a fair dice. So each of these values have about the same probability of showing up. We saw this before when we were calculating expected mean, that the probability of getting any one of these outcomes is 1/6. Notice again that our mean value of 3.5 right here in the middle, so half of these outcomes are greater than the actual mean, and about half are less than the mean. Again, we would also expect to see this. If we make a histogram of the mean values of each group of 5 rolls that we made, we get a normal distribution. Again, 3.5 here in the middle, that's our expected value. About half of the distribution you can see is greater than the mean value, and about half is less than the mean value. So that expected value that we get for the mean value of the population turns out to be, again, the mean value for the sample, for the sampling distribution of the mean values. And so we see that that mean value for the sample is very much like the mean value for the population because we've got a sample size that's big enough to represent the actual population. So we make that histogram for our mean values, we get a normal distribution. Note that in each case, okay, we're targeting 50% as we would expect. So again, half of our outcomes are greater than the mean, and about half of the outcomes are less than the mean. It's not exactly 50, but it's close enough for government work. So notice we also get a normal histogram for the proportion of groups of 5 outcomes. So if we looked at the proportions, so that, that fraction or that part, that percentage that's above or below the population mean, we'd get the same numbers coming out. We'd see about 50% that are above the mean value, and about 50% would be below the mean value. So if we look at a sampling distribution of the sample means, which is essentially that histogram that we saw just a little bit ago. So the sampling distribution of the sample mean is the distribution of all sample means that are possible with all samples having the same sample size taken from the same population. And that's essentially what we were looking at. We were sampling sample size of 5, and we took all those different samples of 5 for the dice rolls that we had, and we took the mean value for each of those samples, and we put them together here into a histogram, and we see that it makes a normal distribution. So in our dice roll experiment, our sample size was 5. We took those samples from the same population, and we saw that the sample mean targets the value of the population mean. What that target word means is that as our sample size increases, the mean value becomes equal to the population value for the mean. So that's what we mean when we say target. The sample statistic starts to equal the population parameter. And that's what we saw with our simulation, that the mean of the sample means after about 1,000 rolls of the dice became pretty much the same as the population mean. And the expected value of the sample mean was the same as the population mean. So that means that the distribution of the sample means tends to be a normal distribution. And of course, we've got the same thing going on with proportions. So if we made a sampling distribution of the sample proportions, we would see exactly the same thing. It would come out to be a normal distribution where approximately half of the distribution is above the mean and approximately half is below. If we look at a distribution of the sample variances, we see something a little different. We don't see the normal distribution. What we see is a skewed distribution. And keep in mind, those pure statisticians, they look for where that larger tail is. So here they would say this is a distribution skewed to the right. Now, the variance for an infinite number of outcomes is going to be 2.9. So our sample size of 10,000 trials better targets the population variance than the 1,000. But again, we see that for the mean value of our distribution, even though it's skewed, we still see 50% of the distribution below the mean, 50% above. So a sampling distribution of the sample variance is simply that distribution of all possible sample variances with all samples having the same sample size taken from the same population. And that's what we've just seen. So we see that the sample variances, just like the means, also target the population variance. We have the mean of the sample variance, the same as the population variance, and the expected value of the sample variance is going to be equal to the population variance. So this is pretty much the same things we saw with means and proportions, with the caveat that the distribution of the sample variances is going to be skewed to the right, as again viewed by a statistician, because me and my friends in industry, we look for where the numbers are. We would say that's skewed to the left, but your assignment problems are going to be written by the pure statistician that wrote your textbook. So you need to be looking at it like that when you're answering those questions. This is going to be skewed to the right. Look for that larger tail here on the end of your distribution. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.